one who's monitoring.
Yes, yes.
Okay, so welcome to the second week of this inaugural series of talks for the FC Kohli Center. So today it's a privilege to have Nima Arkani-Hamed speaking. He is a professor at the Institute for Advanced Study in Princeton, and he's one of the leading quantum field theorists and particle physics phenomenologists of his generation. So Nima has won the Gripov Medal in 2003 and the Sakurai Prize last year. In 2012, Nima was awarded the inaugural Fundamental Physics Prize for original approaches to outstanding problems in particle physics, including the proposal of large extra dimensions, new theories for the Higgs boson, novel realizations of supersymmetry, theories of dark matter, and the exploration of mathematical structures in gauge theory, scattering amplitudes. So today he's going to talk to us, as you can see on the screen, about space-time, quantum mechanics, and the vacuum. Over to you, Nima.
All right. Well, I'm really delighted to be able to join you guys and talk about this, what's really the heart of the subject matter of fundamental physics. And really, there are two main things I want to do in this talk, and if we have time, we'll get to a third. The first thing, I just want to summarize where we've gotten to in fundamental physics now well into the 21st century by reminding you about the 20th century revolutions, which were of quantum mechanics and space-time. And there's this theoretical framework, quantum field theory, that lets us talk about worlds that are compatible with the principles of quantum mechanics and space-time. And the first message, which is I think not widely enough appreciated, even among physicists, never mind outside physics, is how these two principles are astonishingly restrictive and largely dictate the grand architecture of physical laws. And really, the beef of fundamental physics is really constantly about seeing this tension and resolution of the tension between quantum mechanics and space-time. And these grand principles are never far away from the action when you're working on anything in this business. So that's the first point that I want to make. And that makes all the more jarring the second set of points, which are what the storm clouds are. Again, here we are well into the 21st century. And they have to do with the fact that these astonishingly restrictive and successful ideas are likely to be superseded and replaced with something that might eventually look quite different. So the notion of space-time is likely doomed because of gravity, because of effects of quantum mechanics and gravity. There may even be limitations to quantum mechanics when we start attempting to apply the laws of quantum mechanics, not to individual experiments, but to the entire universe in quantum cosmology. And closer to home, there's a very simple question. One of the most obvious facts about the universe is that it's big. So the universe is big and it has big things in it, even though it's made out of microscopic constituents with fundamental laws given at tiny distances. So it turns out we have a terrible answer to the question, why is the universe big with big things in it? And these two mysteries might even be related to each other. So those are the sort of main storm clouds that are driving work in this subject in one way or another. And as I said, if we get to it, I'll say something about a speculation, which has certainly directed my own research over the last 10 years or so, which is that we'll come to see these grand ideas, these big principles of space-time as quantum mechanics, as actually emerging hand in hand from more primitive mathematical ideas. Okay, so let's get to it. First, let me tell you about space-time quantum mechanics and how these two principles make the grand architecture of physical laws largely inevitable. A quick reminder to those of you who aren't physicists, the world around us is made out of matter. We have atoms with electrons whizzing around protons. Protons and neutrons and nuclei. If we look inside the protons and neutrons, we'll see that they're not point-like elementary particles, but they're also made out of apparently point-like constituents. The electron is an apparently point-like constituent. We haven't seen any substructure to it, but the proton and neutron definitely have substructure, and they're made out of point-like constituents that are up and down quarks that are held together inside the proton. They can't get out by the gluons. And we have four basic interactions: gravity, electromagnetism, and the weak and the strong interactions. Gravity and electromagnetism were known to the ancients. The weak and the strong forces began to be known in the very, very late 1800s, early 1900s. The weak interactions are associated with radioactivity. The strong interactions are what hold the earliest incarnation of them was a question of what held protons together in the nucleus of the atom, even though the Coulomb repulsion, the electric repulsion, wants to drive them apart. Today, we know that that is a subsidiary effect of a more fundamental set of interactions that act on the quarks and the gluons inside the protons and the neutrons and trap the quarks and the gluons inside. And a residual effect of that is this attraction between protons and neutrons that keeps them all in the nucleus together. Now, a remarkable thing that we've learned is that there's a fundamental similarity between all these interactions, and they're all associated with elementary particles, basic interactions involving elementary particles meeting at a point in space-time. So the electromagnetic interaction is associated with two electrons meeting a photon. The gravitational interaction between electrons and the gravitational force between two electrons, let's say, is actually mediated by this fundamental interaction involving two electrons and a graviton. And if we concatenate these fundamental processes over and over and over again, we get all the processes that take place in the world around us. So electrons scatter off each other. In the simplest way, we imagine that they exchange this photon, that they excite a virtual photon out of the vacuum. But more and more complicated processes just come from gluing these basic fundamental interactions together. And something that was not obvious at all, but became eventually obviously true in the development of the famous standard model of particle physics, is that all of the interactions have the same structure. The strong interactions are associated with exactly the same basic interaction between quarks and gluons. The weak interactions are associated with exactly the same kind of pictures again, now with other kinds of cousins of the photon, W particles and Z particles. It's the same basic interaction. There are what from the fundamental short distance point of view look like detailed differences that make a very large difference when we look at physics at very long distances or concomitantly very low energies. For example, the photon is massless. And so if I try to excite a photon out of the vacuum, it's easier. It's harder and harder to make it to make an excitation that's relevant over very long distances, and that's why the electric force between electrons dies off as the inverse square law. Or if I have the graviton exchange, it would also die off as an inverse square law. However, it would be much worse if the particle was massive. It wouldn't just die off as a power law, it would die off exponentially. And that's what happens with the exchange of W and Z particles, which are massive. So that's why electromagnetism and gravity look like they're associated with long-range forces, because the corresponding particles are massless. But the weak interactions are associated with a short-range interaction of around 10 to the minus 16 centimeters. Another feature of these of the elementary particles is that they have spin, and the spin is quantized, like everything is quantized in quantum mechanics, and they come in multiples of 1/2 times the Planck constant. So the allowed spins that you can have just from quantum mechanics are any multiple of a 1/2 h bar. But the menu that we see, the electrons have spin 1/2, the W particles have spin 1, the photon and the graviton have spin 1 and spin 2, respectively. But the menu is extremely simple. All the familiar things that we know of just come from these three possibilities: 1/2, spin 1, 1/2, spin 1, and spin 2. Okay, so and in fact, here is the menu of all the elementary particles there are and the basic interactions they have. We're not going to go through this table in any detail, but suffice it to say that this table really contains everything there is to know about the structure of the standard model of particle physics. We have quarks and we have leptons. The interactions are mediated by gluons, W particles, and W's and Z's, and the photon, which are sort of mixed together the so-called electroweak interaction, and the graviton. And so, this menu just tells you which stick figures you're allowed to draw, which basic 3-point couplings you're allowed to have, and the interaction with gravity is universal with the universal strength. Okay, so this particular set of elementary particles and interactions is what governs fundamental physics, certainly down to the distances that we've probed so far, which is around 1,000 times smaller than the nucleus of the atom, around 10 to the minus 17 centimeters. Those are the distances that are being probed at giant accelerators like the Large Hadron Collider. And this structure holds sway all the way from there, and perhaps even much shorter distances, will come to that, all the way out to the size of the observed universe, around 10, 15 billion light years. Now, but what I want to get to is something more structural. I want to explain, why did it turn out to be so simple? Why are the fundamental, I mean, this might not seem terribly simple. This menu is not terribly simple, but it's certainly not extremely complicated. And it's remarkable that it all comes down to this basic, simplest interaction with this tiny menu of spin. So that's what I want to now sketch an explanation for. Why do we only have simple fundamental interactions that involve 3 elementary particles meeting at a point? I told you that we concatenate these interactions over and over again to get everything there is, but why weren't there fundamental 12 particle interactions? That would, of course, make it impossible to explain, to reduce the complexity beyond beneath 12 particle scattering. Didn't turn out that way. We only have the basic interactions are just 3-point scattering, and all the other interactions are derivative from that. And why do we have only such a tiny menu of spins? And so what I'd like now want to sketch for you is an argument that in one way or another, people have known for maybe 40 years, but I think it's been increasingly appreciated with time. And as I said, it's not widely appreciated even for most physicists, never mind beyond physics. I want to, so what I want to explain is that whatever the ultimate theory is, which we don't know what it is, but so long as it agrees with the principles of space-time and quantum mechanics, it's guaranteed on general grounds that at long enough distances, you'll see a world described by some finite number of species of elementary particles interacting with a fundamental 3-point interaction, and that the only allowed spins are for elementary particles are spin 0, a half, 1, 3 halves, and 2. In other words, if you locked up sufficiently competent theoretical physicists in a room, you didn't let them see the world outside, you just handed them food and graduate students and the principles of space-time and quantum mechanics, they would discover that at first they would think it's impossible to make them consistent, but after they worked for a while, they would discover this very small set of possibilities. They'd also discover that this massive spin-do thing is unique, and that if there are massive particles around, it would make it go around in orbits. It's gravity, but they haven't seen gravity. They haven't seen Newton's apple fall. They haven't experienced Einstein's falling elevators. In fact, they would discover not only is it gravity, but that it's the theory that describes it has to be general relativity to some leading approximation. And they would discover that without knowing anything other than the principles of special relativity, space-time and special relativity, and of quantum mechanics. And I put in red here, so the familiar elementary particles that we know of have these spin 1/2, 1, and 2, but you see there are these interesting 2 other possibilities of spin 0 and spin 3/2 that I'll say a little bit about. All right, so that's what I want to explain is why is this the case? At least sketch out why is it the case that we have only simple fundamental interactions with such a tiny menu of spins. And to begin with, we're going to go back to something very, very basic and talk about units. This is the bane of the existence of many high school physics students. Certainly it was of mine. And part of the reason units are so annoying is that they're human constructs. So the first thing to do is to talk about natural units. In order to do that, we make use of the fact, going back to Max Planck, that we have constants like the speed of light and Planck's constant in quantum mechanics that let us convert distances to times via the speed of light and convert energies into times via Planck's constant. And in this way, we can reduce all units to one unit. We can make that unit, for example, a unit of mass or energy. So we say in choosing natural units that we put h bar and c to 1, but just so I give you an idea of what these units look like, the size of a proton is units of length. Length has units of 1 over, the length has the same units as time. Time has units as 1 over energy. So a length has units of 1 over energy. Okay, so the mass of the proton is what we'll use as our unit. It turns out to be very close to 1 giga-electron volt. Okay, so if it was up to me, I would just define a giga-electron volt to be the mass of the proton. But then in these units, the size of the proton, which is around 10 to the minus 14 centimeters, would be 1 over a giga-electron volt. And now we could talk about more familiar things in these units. For example, my height. I'm around 10 to the 16th inverse GeV. And you see, that's a very useful way of characterizing my height. You could describe how tall I am to someone who lives in Mars, who's never been to Earth, instead of saying I'm about 1.5 meters tall, which means that if you put me end to end next to this bar in Paris, the ratio of my length to the bar in Paris would be close to 1.5. They've never seen that bar in Paris. Instead, if you say that I'm 10 to the 16th the inverse GeV tall, they'll know what that means, because it means if they stack 10 to the 16 protons on top of each other, get around my height. Similarly, my mass is 10 to the 29 GeV, and that's also useful. It tells you that I'm made out of around 10 to the 29 protons and neutrons. And if you're lucky, the rest of this lecture time will be around 10 to the 27 inverse GeV. And an inverse GeV, because that's the, it's 10 to the 27 times how long it takes for light to traverse the distance of around the size of the proton, and so on. All right, so we only have this one unit, but now let's return to some very basic things that you probably all remember from high school physics. So if we look at the electric force between two electrons, we know that it goes like some charge squared divided by r squared. But now if we use what we just learned about the units, remember force has units of mass times acceleration, and that is units of 1 over length squared. Okay, so there's a 1 over length squared already here, so we learned something interesting, that this coefficient q squared is just a pure number, and that's around 1 over 137. That's its famous fine structure constant. On the other hand, if I look at the force between two electrons, it's g Newton times their masses over r squared. So that tells us that g Newton m squared is dimensionless, but g Newton itself has units of length squared. And in fact, that's what it is. G Newton in these natural units is 10 to the minus 33 centimeters squared. That's its famous Planck length squared. 10 to the minus 33 centimeters is ludicrously tiny distance compared to any distances we've probed. As I've said, the tiniest distances we're probing at accelerators is around 10 to the minus 17 centimeters. So the tininess of this 10 to the minus 33 centimeters of this length scale associated with gravity of the Planck length relative to normal human length scales is a reflection of the extreme weakness of gravity compared to all the other interactions. And 1 over L Planck, yes.
Can I interrupt you? I'm not a physicist at all, so I might be asking you a very stupid question. I got excited by the fact that you said this is school physics. So, you know, like the fact that you're talking about electric force here. Electric force, I mean, it's a force. So, I mean, school physics tells force has some unit, right? I mean, it's mass into acceleration, so it has to be, you know, some unit of mass into meter per second square or something.
Exactly, exactly, yes, exactly. So that's just what I converted that for you is something in natural units. So as you say, it's mass times acceleration. So what is acceleration? Is velocity over time. Okay. So what are units of velocity? Velocity is dimensionless in these units. Okay. If I want to say that that something is moving at 3 meters a second, what is that? There's a dimensionless number there, which is around 10 to the minus 8, okay? Because that's 10 to the minus 8 times the speed of light, okay? So the velocity is dimensionless. So any velocity is just given by a dimensionless number. So acceleration has units of velocity over time, so that's 1 over time. Mass has units of energy, which is also 1 over time in these natural units, or 1 over length, because I can convert between time and length. So you see that force has the same units as 1 over length squared, okay, or the same units as mass squared. Okay, so that's what's beautiful about these natural units is you can convert every unit. You don't have to remember all the stupid units. You can convert every unit to this basic one. And then when you do that, you discover some interesting things, that that the electric force is actually associated with a fundamentally dimensionless parameter, 1 over 137. That's small. Whereas the gravitational force is not. The gravitational force is associated with this dimension full parameter, and therefore to say whether gravity is weak or strong. So you see, in an invariant sense, electromagnetism is weak because the strength of the interaction is a small number, around 10 to the minus 2. 1 over 137, but not true for gravity. Gravity is astonishingly weak when the distances are much larger than 10 to the minus 33 centimeters, but conversely becomes very strong when the distances become comparable to 10 to the minus 33 centimeters, or the energy becomes comparable to this Planck energy of 10 to the 19 GeV. The only reason we notice gravity, despite its extreme weakness, is it doesn't cancel out compared to all the other forces, of course, which do cancel out. But already, if you take a pair of hydrogen atoms and hold them a millimeter apart from each other, the residual electric forces between them, known as the van der Waals force, is already stronger than gravity at around that scale. So that gives you an idea of how ridiculously weak gravity actually is. Okay, so did that answer your question?
Yes, I think that's the best way under the circumstances.
Okay, well, we can come back to it at the end of the talk. Okay, so, all right. Okay, so all right, so much about units. Now let me remind you of another aspect of that becomes obvious from these units. If we think about the basic process involving the collisions of particles, quantum mechanics tells us that we can't predict exactly what happens, exactly what comes out. We can only predict the probability, but the probability is given as the mod squared of a certain amplitude, of what's called the probability amplitude. And so if I talk about the scattering between 2 electrons, I learn from here, it's got to be, again, this sort of basic process at some leading order. And the amplitude goes like, again, this charge here and a charge there goes like q squared. This is around 1%. And so, again, in a fundamental sense, the amplitude for the scattering is small. But that's not true for the exchange of gravitons. If I have a scattering between electrons, there's a gravitational component to it. Now this amplitude goes like g Newton times the energy squared. And so it's tiny when the energies are very small compared to this Planck energy, 10 to the 19 GeV. But if I extrapolate this formula, when the energy becomes larger than 10 to the 19 GeV, it blows up. And so therefore, already from here, we know that something new has to happen when the energies are comparable to 10 to the 19 GeV, around this Planck energy, because it doesn't make sense for the amplitudes to get bigger than 1. Probabilities cannot be bigger than 1. Something new has to happen at or beneath this energy scale. All right, so with that introduction about units, we can now understand something about a very important notion of effective theory. So let's go back. If we look, for instance, at the basic interaction between electrons and photons and quarks and gluons, and all the other ones that I mentioned in the standard model, except for gravity, all of these guys are associated with small dimensionless constants. There's some detailed differences. This guy is around 1 over 137. This guy, around the energy scales that we probe it, is around 1/10, but they're still relatively small dimensionless numbers. On the other hand, imagine we had some interaction that involved, let's say, more photons coming out. Now, remember, I told you that already the fact that we get an inverse square law, I mean, it does die off with distance. So that means that just exciting one photon out of the vacuum is costing you something. It's harder and harder to do it as you go to longer and longer distances. And therefore, exciting 2 photons, 3 photons out of the vacuum is going to be harder still. You'll have more and more powers of 1 over length as you pull the electrons apart, further and further apart from each other. And that tells us, by that very simple dimensional analysis, that the strength of any one of these interactions that involves spitting out more photons has to actually have a positive power of some length scale in it, again, just by units. So all of these interactions, if I have more things coming out other than just 3, all of them have a strength that goes like some length scale to a positive power. And what that means is that as long as you go to distances that are long compared to that length scale, they will be irrelevant and tiny compared to the leading interactions you can have that are the very, very simplest ones. So that tells us that at low enough energies, only this basic ABC type interaction will be relevant. Okay, so that's the first thing. Sorry. Yes.
Yeah. Is that why you said that you cannot have something like with 12 particles interacting?
Exactly. This is the explanation for why we can have something with 12 particles interacting. In fact, it tells us more. It says that even if there was, in some sense, some fundamental 12 particle interaction, it would be irrelevant. You wouldn't notice it at long distances. What would dominate the world at long distances are the very simplest interactions. Okay.
Oh, thanks.
So that's the explanation for that point. Now let's talk about why there's such a tiny menu of spins. And first, we have this attitude that we're going to describe physics at very, very short distances first. That's the basic reductionist paradigm. And at very short distances, because of quantum mechanics, means very high energies. And so what we want to do is, if we're imagining particles smashing into each other at very high energies, clearly we should be able to ignore their mass in first approximation. I'll come back to this important point in a second. There's a footnote to this point, which is the entire story of the Higgs particle. But to begin with, we're going to just think about the particles as being basically massless. Now, when the particles are massless, there's something very important, that the spin that they have, we can only talk about their spin either in their direction of motion or opposite to the direction of motion. I'll come back and explain this point a little more later. So the spins that they have are, you can also call helicity, or from high school physics, maybe the polarization of electromagnetic radiation. Okay, so we can think of it as how they spin either in the direction of motion or opposite to the direction of motion. Okay. All right. So now let's come back and imagine that what you might think of as the simplest a collision between the simplest collision process, which is 2 particles in and 2 particles out. And let's think what we can say about this interaction on general grounds without knowing anything else. Well, this amplitude, whatever it is for the scattering process, can depend on the energies of the incoming particles and on the angle that the outgoing guys are going out in. So in principle, it depends on a lot of things. An energy and an angle, you could imagine writing down complicated functions of energies and angles. And in fact, the actual amplitudes of 2 in and 2 out do have some complicated dependence on energy and angle in general. But this is not the simplest scattering process you could imagine. The very simplest scattering process you could imagine is the one that we've talked about, where you have a particle coming in and splitting into 2 other particles. Now, here's the crucial point: if particles are massless, then this splitting, then by conservation of energy and momentum, the particles B and C that are going out have to be pointed in exactly the same direction as the particle A. All you can do is take the initial momentum and split it at some fraction going into B and going to C, but there's no angle. Okay, so there's nothing complicated. There's no complicated dependence on angle because there's no angles at all. Furthermore, it can't depend on the energy. And the reason why it can't depend on the energy is that by boosting to a different frame of reference, you can make the energy change. And yet special relativity will tell you that the amplitude should not depend on the reference frame. So there's no dependence either on energy or on angle. Yes, sorry.
No, I mean, so it could be, theoretically speaking, in principle, it should be possible that, you emit 2 particles, but they go in the opposite direction and maybe with different velocities, and that would still conserve the momentum.
Except because the particles are massless, they have to move at the speed of light. That's the point. Because they're massless, they're always moving at the speed of light, and so so this is where relativity plays an important role, and that's why I say this is dictated by the principles of space-time. But you see, what's really cool is it can't depend on energy or angle, and therefore it's completely fixed by up to overall strength of the interaction, the number that goes with it. It's completely fixed just by giving the spins or the helicities of the particle. There's no other data that it can depend on. Okay, Now, so once you take that, now we can go back to the 4-particle process. And now there's actually an important constraint on 4-particle scattering, which is that when the energies of the 2 incoming particles A and B are such that they could actually produce a real intermediate particle E, then we should have a resonance. Okay? And this is a very familiar phenomenon of resonance, that when you excite a system at the natural, at one of its natural frequencies, the amplitude becomes large. So here we should expect that if particles A and B satisfy that the momentum, the energies and momentum of A and B can add up to some E in the middle, the amplitude should blow up. But how it blows up should be dictated by the product. You should interpret that blow up. This is the principles of quantum mechanics now. Quantum mechanics tells you should be able to interpret that blow up as actually producing particle E, and then having particle E travel some distance and decay to C and D. So this is a mathematical constraint on this function. This function can have poles, can have singularities, in the simplest case can have poles, but the residues on those poles have to factorize into the product of these 2 simpler amplitudes. And remember, I just told you by the principles of space-time that these amplitudes are actually completely determined up to the strength of the interaction. So this is an interesting mathematical constraint. You have to write down some function of energies and angle with poles which factorize properly on the poles in this way. And now all you have to do is solve this mathematical problem, and it's a very simple problem to solve once you have the right very simple formalism. In about a year of grad school and about half a page of algebra, or maybe 1.5 pages of algebra, depending on how big you write, you discover the following amazing thing, which is that the only possible solution to that consistency condition involving 4-particle scattering tells you that you can't have any old spins. The only particles you can have spins 0, 1/2, 1, 3/2, and 2. Okay, and so therefore, just the laws of relativity and quantum mechanics have reduced all the complexity of the world down to just choosing a menu of these guys and the strength of their interactions, and that's it. And as I mentioned before, the spin 2 guy is unique. You discover you can't have more than one of them. You can have only one of them, and their interactions are universal. They have universal strength coupling to everyone. It's gravity, but you discover that as just one of the solutions of this, of this simple mathematical consistency condition that incorporates in the most direct way the principles of space-time and quantum mechanics. You discover you can have particles, massless particles of spin 3/2, but remarkably, you can have at most 8 of them. And I'll come back to say a little bit about this in a moment. You can have particles of spin 1, but the interactions they have to have the famous Yang-Mills structure. But it has nothing to do with the beauty of group theory and symmetries and so on. It's just one of the solutions to this beautiful little problem of consistency of relativity in quantum mechanics. Similarly, you can have any number of these particles of spin 1/2 you want. If there are spin 1 guys around, they have to interact with them in a particular way. Similarly with all the higher spins. And spin 0. I've put in red 0 and 3/2 the spins that are not those of familiar elementary particles. We'll come back to the spin 0 in a second. But remember, electrons and so on have spin 1/2, photons and W's and gravitons of spin 1, and photons and gluons and so on have spin 1. The graviton has spin 2. All right, so what I've told you is that, again, the sort of grand architecture of the laws of physics are basically determined by the principles of space-time and quantum mechanics. There is one footnote, which is about the story of the Higgs particle. And the footnote is that at the very start of the discussion, I said that, well, when we go to very high energies, we should be able to ignore the masses of the elementary particles. But there's actually, that's not as innocent as it seems. You can't be a little bit massive. It's like being a little bit pregnant. And that's because of this amazing difference between massive and massless particles with spin. Let's say you have a massive particle of spin 1, like the W particle. What that means is no matter how fast it's moving, I can always go to a frame to catch up with it. And if I catch up with it and I see it spinning up, by tilting my head, I can see it spinning in all 3 directions. So rotational invariance tells me that a spin 1 particle has to have 3 possible ways that it can spin, 3 spin degrees of freedom. On the other hand, a massless particle, I can never catch up with it. And therefore, I can never decide, I can never do this tilting my head to see it spinning in all possible ways. And that's why massless particles only have 2 spin degrees of freedom, not 3. Okay, so there's 1 extra guy. If you have particles with spin, there's really 1 extra guy degree of freedom associated. And so when we go to very high energies, we have to keep track of that. In fact, if you imagine a massive spin 1 particle like the W particle that we had talked about, and imagine that it's spinning in some direction orthogonal to the way that we'll eventually boost it, then it's sort of intuitive that the amplitude to find it spinning in these orthogonal directions should not depend on how much I boost it. But again, by a dimensional analysis, if it's spinning in the direction in which you boost it, the amplitude to find it in that state does grow, and it can grow like the energy divided by the mass of the particle. So this is the new extra guy that we have when we go to very high energies, and we see that the kind of the possibility of it spinning in the longitudinal direction, the direction of its motion, means that even if the basic coupling constants are dimensionless, because of this sort of kinematic fact that the amplitudes involving the longitudinal components might still grow. And in fact, this is exactly what happens if we take the scattering between these W particles. The amplitude between the normal guys that have like helicity, the ones that would be there if it was just massless, their amplitude has the same Q squared in it, which is about 1%. But the amplitude for the longitudinal guys, they still have the Q squared from these couplings, but they have this kinematic piece that grows like the energy over the mass squared. And so even though this number is around 1%, when the energy over mass becomes around 10, the amplitude becomes of order 1 again, and something bad has happened. Again, we have the same problem. When an amplitude is of order 1, the probabilities are threatened to be bigger than 1. Something new has to happen. And the mass of the W particle is around 80 GeV, 80 times the mass of the proton. And if you put the numbers in a little bit of detail, something new has to happen when the energies are around beneath around 1200 GeV. And so from the first part, just by units, you might have thought that the story was that we have all the particles that we've seen, we go to very high energies, we can ignore their masses, and then maybe something very new is happening near the Planck scale, 10 to the 19 GeV. But in fact, that's a naive expectation if we could just ignore masses because we go to high energies. But the actual situation is that something new had to happen beneath around 1000 GeV that was much, much closer to home. Okay, way before we get there. And what is that new thing? Well, you need something new. Some other thing has to come in order to solve this problem. And what's the menu of possibilities you can have for this new thing? Well, it has to interfere. It has to add to these processes that we talked about and fix this issue up somehow. We go through the menu of possibilities for what it could be, and you can definitely cross out all the possibilities of spin 2, 3, 4, and above. Spin 1 was maybe a possibility for a while, but it had other detailed problems. So the only thing and the simplest thing that could be is just a particle of spin 0, and that's the Higgs particle. Okay, so that's the story of the Higgs, is that we needed something to allow us to be able to interpolate between the world of massive particles at very low energies and this very rigid set of theories for massless particles at high energies. And just the degree of freedom counting did not work. If we just took the massive particles that we knew, we couldn't reassemble them into these consistently interacting massless theories at very high energies unless we added something. The amazing thing is that all it took was a single degree of freedom. 1 elementary particle was all it took in order to allow this to happen. And at very high energies, this extra Higgs particle, together with these additional longitudinal components of the W and the Z particles, unite into objects that have exactly the allowed kind of interactions for massless particles. Okay? So finally, with the Higgs, we have in our hands a theory that we can extrapolate to much exponentially higher energies without running into any internal theoretical inconsistency. Now, the only place we run into a theoretical inconsistency is when we go all the way up to the Planck scale, where, as I mentioned before, now we have those problems involving the gravitational amplitudes becoming large. And so the story of the Higgs is really a sort of a triumph for this theoretical structure, because you look at the menu of possibilities of what you're allowed to do. You're only allowed to choose from this menu of particles of spin 0, 1/2, 1 3/2, and 2. And the thing with spin 0 actually solved this theoretical problem of the interpolation between massive particles at low energies and massless at high energies. And famously, 10 years ago, on July 4th, 2012, the Higgs particle was discovered at the Large Hadron Collider, where protons are collided at 0.9999999 times the speed of light, probing distances around 1,000 times smaller than the nucleus of the atom. And I won't explain this plot, but there it is. It was a triumph for experiment, a triumph for theory, and an indication that these basic fundamental principles of space-time and quantum mechanics works. And that's why the Higgs is such an exciting particle. It's really the first really new elementary particle we've seen. It's the first example of the simplest possible elementary particle of spin 0 that we've seen before. And even though I'm running very short on time, I hope I'll get to say a little bit about it. That very simplicity is what makes it so perplexing at the same time. So now we've turned this red into black. We've now seen nature make use of this possibility as well. Now the only thing that we've not yet seen nature make use of is the possibility of elementary particles of spin 3/2. That has to do with the notion of supersymmetry, and I'll come back to that again if I have time in a little bit. All right, so that was a review of where we've gotten, but even though many of you have probably seen some aspects of this story, the standard model, the story of the Higgs and so on, I'm trying to explain it to you from a point of view that makes its connection to the basic principles of space-time and quantum mechanics as direct as possible. Because again, that's the entire drama of this subject constantly is the tension between these two ideas. And so that's why I wanted to recap that story from this point of view. All right. So now let's talk about some of the, the main storm clouds. First, we have this notion that the idea of space-time is likely approximate and needs to be replaced with something else. So, and there are very simple thought experiments that indicate why this is the case. So let's say that you try to look at some region of space and time by putting it under a microscope. Well, by the uncertainty principle, you know you have to put higher energy into a smaller region of space in order to probe what's going on at shorter and shorter distances. We need smaller and smaller wavelengths in order to resolve what's going on at small scales, and smaller wavelengths means higher frequencies, and higher frequencies means more energy. That's another way of saying it by quantum mechanics. This is, after all, why we need to build giant machines. That's the irony, that we build these giant accelerators to probe very, very high energies in order to look at the tiniest distances that we've ever seen as in trying to see what's going on with the laws of nature at very short distances. Now, in a world without gravity, all you need to do is build higher and higher energy machines, and you'll probe smaller and smaller distances. But in a world with gravity, eventually something very bad happens. Eventually, you put so much energy into such a tiny region of space. But when you put a lot of energy there, since E equals mc squared, it's like putting more and more mass there. And so at some point, you put so much mass into a small enough region of space, you're going to collapse that region into a black hole. And that makes it impossible to see what's going on in there. Okay. So, and if you get frustrated and try to build an even higher energy machine, you make an even bigger black hole. So that means there's no operational meaning to distances and times. That happens for the first time when you're probing distances around this Planck length. What else could it be? Again, by dimensional analysis, 10 to the minus 33 centimeters. But it means that there's no operational meaning to talking about distances and times that are smaller than 10 to the minus 33 centimeters, 10 to the minus 43 seconds, this Planckian scales, okay? And every time this has happened to us in physics before, that there's some notion we can't even in principle give operational meaning to, it's meant that that idea is approximate and has to be replaced with something else. In this case, it's very dramatic, because the thing which is approximate is the notion of space-time itself. Now, when do these things hit you in the face? They hit you in the face when the curvatures in space and time become comparable to the Planck scale. So for instance, if we run the picture of the expanding universe back in time, we run into the Big Bang singularity. What's going on as we get closer to the Big Bang, so the curvatures are just getting comparable to the Planck scale. So the very notion of space and time is breaking down there. So that's why we don't know what's going on with the Big Bang or before the Big Bang. Even the word before is breaking down when we get close to the Big Bang. Similarly, if you throw yourself into a black hole, there's no center you get sucked into, but there's a sort of moment in time in your future where you get crunched. It's like the opposite of the Big Bang. It's like a big crunch inside a black hole. And again, at that moment, the curvatures are becoming comparable to the Planck scale. And so our theories just break down when gravity is strong and quantum gravitational effects are dominant. There's another aspect of this, which is that it's also an end of reductionism, because the idea that the physics is handed to us at very, very short distances, and then all we have to do is find the consequences of the laws at long distances. Well, the notion of short distance is gone. And in fact, if you scatter particles at energies way above the Planck scale, not only do you make a black hole, but the black hole gets bigger and bigger as the energy gets larger and larger. So higher energies correspond to shorter distances for a while, until the energies get comparable to the Planck scale, and then this starts corresponding to longer distances again. Okay, so the whole notion of reductionism is likely wrong. Another somewhat deeper aspect of these considerations is that there are no well-defined observables that we can quantum mechanical observables that we can meaningfully talk about, that you can measure in some fixed size room, in some fixed size region of space and time. That's because quantum mechanics says that in order to talk about an observable with precision, you have to do the experiment over and over again, because quantum mechanics only talks about probabilities. But also you have to divide the world into a measuring apparatus that in principle can become as large as you want, in order for the measuring apparatus not to have its own irremovable quantum mechanical fluctuations. So you have to have a world where you do infinitely many experiments, but with an infinitely large measuring apparatus that looks like at a finite system. And in a finite size room, you can't do that, because if you make the measuring device bigger and bigger, it inevitably gets heavier and heavier. And before it becomes infinitely big, it becomes massive enough that it collapses the whole room into a black hole. And then you're sucked into the singularity, and you can't do the experiment over and over again either. Okay, so there are no local observables when you have, there are no well-defined local quantum mechanical observables. Now, there's some degree of imprecision associated with any local observable, which is super exponentially small. That's why this is kind of practically irrelevant for almost all, for any purpose. But conceptually, it matters a lot, because it means that there is no well-defined sort of quantity in the interior of space-time that we can talk about. And when we have quantum mechanics and gravity, the only things that we can talk about meaningfully live at infinity. They involve experiments that start and end at the boundaries of space and time at infinity, where you can make apparatuses bigger and bigger, but also pull them further and further apart from each other, have them fire particles into the inside of the space-time, they bang into each other and come back out again in some way. Now, this was the kind of program of thinking about the possible consistency of particle scattering, even including gravity, got a huge shot in the arm in the 1980s with string theory, which began as a theory for the these observables that involve scattering of particles in flat space, like not so different than the experiments that we actually do at accelerators, where particles come in from far away, bang into each other, and go out. And of course, famously, people discovered that to come up with a consistent way of describing those scattering processes, so these gravitational amplitudes that we talked about don't blow up, you actually have to think of those little particles as little loops of string instead. In the late 1990s, people discovered another avatar and a more complete and in many ways a deeper avatar of these observables at infinity by talking about a slightly different kind of universe. Physicists love putting things in boxes. The closest you can come to putting a universe in a box is the following kind of geometry that's known as AntiDeceiter space. It really looks like a tin can as I've drawn it, but the geometry inside the tin can is warped. And it's warped in such a way that if I take a point on the inside, the distance to the wall of the tin can is infinite, but light takes a finite amount of time from the middle to bounce off the wall and bounce back. Okay, so that's the sense in which it's the closest thing we can do to putting the universe in a box. And you imagine if you lived in AntiDeceiter space, you would still get to ask what are the well-defined quantum mechanical observables. They would still involve experiments you can do that start and end at infinity, where you ping the walls of the box and have waves coming inside the interior and crashing into each other and going back out again. But what people discovered in the late 1990s in string theory at first, and then it's a much more general idea that's been evolving a great deal ever since, is that since the observable starts and ends on the walls of the box, you might wonder if there's a theory that lives just on the walls of the box that never talks about the interior of the box, that actually calculates this observable. And there is, and remarkably, it's a completely ordinary quantum field theory that just lives on the walls of the box, that just involves particles not so dissimilar from the quarks and the gluons, but interacting with each other so strongly that you can't follow what the individual particles are doing, but only what aggregates of appropriate averages of them are doing. But the kind of the description of this strongly interacting system of cousins of quarks and gluons is exactly like a hologram encoding a theory that has gravity and even strings and extra dimensions and all that stuff in the interior of this AntiDeceiter space. So amongst other things, so one of the slogans is the world as a hologram. Another one is that string theory and particle physics are much more closely tied to each other than they appeared at first in the 1980s. However, as wonderful as this progress is, we don't live in this kind of universe. We don't live in a universe in a box. And in fact, the sort of deepest facts about our universe are cosmological. We already talked about the sort of existential question of what happens at the Big Bang. Similarly, so the notions of space and time are breaking down near the Big Bang. See, in this picture, the notion of time is not breaking down at all, but this is an infinitely old, this is an infinite tin can that exists forever, eternally, and so the notion of time in particular is not emerging. The time that flows on the outside of the box is the same as the time that flows in the interior, but that's the notion of time is the most fundamental, deepest one in our own universe. The notion of time likely breaks down when we head towards the Big Bang. And there's even another set of challenges, maybe the sort of biggest challenges in fundamental physics, that the problems are so hard that I have no idea that the timescale on which progress on these problems will be made. But it has to do with the fact that our astronomers discovered also in the late 1990s that our universe is accelerating. And that means something remarkable, that what we see now in the universe is what we're ever going to see. We're not going to see more, because light from sufficiently far away regions just will never make it to us. They're trying to make it to us, but the universe is doubling in size every 10 billion years. And so that means that just twice as much space is being generated, or 2 cubed as much space is being generated every 10 billion years. And so that light will just never make it to us. So what we see now in our universe is what we're ever going to see. And that imposes on us, for the first time in physics, a fundamental finiteness. And remember, I told you, quantum mechanics demands that you divide the world up into an infinite measuring apparatus and a finite system that's being looked at. But this sort of funny artificial division into infinite apparatus and finite system is simply impossible in our current accelerating universe because of the fact that everything is fundamentally finite. Okay, so it's huge, but it's fundamentally finite. And so dealing with these questions is not just understanding sort of the emergence of space and gravity and so on, which is already spectacular in this picture, but we have to understand the emergence of time and also possibly an extension of the rules of quantum mechanics, because finally, for these questions, for the first time, the formalism of quantum mechanics, what it takes to discuss quantum mechanical observables in a consistent way, needs to be modified or extended in some way. All right, so that's the first set of questions about the doom of space-time. So let me now at least sketch something about the second set of questions that are closer to home in many ways, which is this this very simple seeming question: why is the universe big? And there are two features to why the universe is big that or two aspects of it that I want to talk about. Well, one of them is the most obvious one: why is it big? You know, why do we have this nice big universe? We can see out a very long way. We can see out 10 billion light years. Things are more or less the same there as they are here. So why is it big? Even though the basic elementary particles are, well, point-like, but the fundamental scales, like the Planck length, there's this minuscule length scale. The laws of nature, you know, the basic laws are given to us at tiny distances, yet we have an enormous universe. And this universe has big things in it, like you and me and elephants and the Earth are large objects living in this large universe. Okay, so you would think such a simple question in the 21st century would have a great answer to the question, why is the universe big, with big things in it, but we do not. Okay, and this now has to do with the vacuum. Which has to do with the quantum mechanics in the vacuum. Again, it's space-time quantum mechanics and the vacuum. And it has to do with the fact that there are quantum mechanical fluctuations even in the vacuum. So if we think about a ball hanging on a string, a pendulum, and ask what is its minimum energy configuration, well, in a classical world, it can be at the bottom having zero kinetic energy. So it has zero kinetic energy, zero potential energy, so its minimum energy is just zero. But quantum mechanically, because of the uncertainty principle, we can't both know that it's at the bottom and that it's not moving. And so there's a minimum amount of jiggle associated with it. And the energy of that minimum amount of ground state, you know, vacuum, lowest energy jiggle is given by Planck's constant times the typical frequency of the oscillation associated with the jiggle. So if we now take that basic logic and we ask for, let's say, modes of the photon. So I take a box and I ask, what's the kind of energy of the lowest energy associated with the excitations of the photon in that box? Well, the typical frequencies of the fluctuations would be given by 1 over the size of the box. So those frequencies are getting higher and higher as the box gets smaller and smaller. The volume of the box is getting smaller and smaller, and therefore there's more and more violent fluctuations as I go to shorter and shorter distances. Okay? That's the basic problem, is that in quantum mechanics you expect increasingly violent quantum mechanical fluctuations as you go to shorter and shorter distances. Okay? So there's this quantity that's known as the cosmological constant, and it's just the energy density of the vacuum. So I can try to estimate it by taking the energy of the vacuum per unit volume. But if I do this estimate by making the box smaller and smaller, I'm making the energy of these frequencies, as I just said, higher and higher. The volume is getting smaller and smaller. And so naively, this energy density is infinite. Well, of course, we can't really make the box arbitrarily small because, as we just said, the notion of space and time and so on is breaking down at the Planck scale. But I can make an estimate for how big this energy density is. It should be around a Planck energy per Planck volume. So there should be a Planckian energy density associated with the vacuum. But what will that energy density do? Well, Einstein tells us that energy and mass curve space-time. So what's the typical curvature of the space-time that will be associated with this Planckian energy over Planckian volume? We don't need to know any formulas to do this. Again, just the dimensional analysis. There's only one word on one scale that is shown up here. That's the Planck scale. And so the curvatures that will be associated with this energy density would be around 10 to the minus 33 centimeters. So this energy density would either curve up space-time, so it had a violent curvature around 10 to the minus 33 centimeters in size, or it might make the universe explosively accelerate, double in size every 10 to the minus 43 seconds. Neither one of these things is remotely what our very comfortable, nice, huge universe looks like. So what the hell is going on? Okay, so we just made an estimate for the energy density, and the estimate gives us, tells us that the world should look as radically different than what it actually looks like as we could imagine. Now, a good theoretical physicist can estimate everything in the world and get it right to a factor of 10. If you're Enrico Fermi, you get it right to a factor of 1.5. If you're Feynman, you get it right to a factor of 3. But a decent theoretical physicist will get it right to a factor of 10. This is off by a factor of 10 to the 120. And we're not used to screwing things up at a factor of 10 to the 120. So what do? Well, this is what we literally do. We say that, well, since we don't see that, the actual energy in the vacuum, it cannot be remotely that big. So there has to be some other contribution to the energy, some sort of classical contribution to the energy density that's sitting there already. And it must be that that's canceling this enormous quantum mechanical correction to very, very high accuracy. How high the accuracy? As I just told you, it's around 1 part in 10 to the 120. Now, there's nothing inconsistent about this. I want to stress this point. There's nothing mathematically or physically even inconsistent about this. It's not like the other problems we talked about, like the amplitudes getting larger than 1, where the probabilities are literally getting larger than 1. That's an actual inconsistency. This is not an actual inconsistency, but it looks very strange. And it's like walking into a room and seeing a pencil standing on its tip to within 10 to the minus 120 degrees of vertical. It's not inconsistent. That's a consistent solution of Newton's law for a pencil to be within 10 to the minus 120 degrees of vertical. But if you saw something like that, you would wonder what's going on. You might look to see if it's hanging from a string from the ceiling, or if you look carefully, if there's a little creature with a hand holding it up, or maybe some other explanation. So we would like to have an explanation of this. And it's just really to answer the really simple question, why is the universe big? Now, there's another aspect of the question of why the universe is big that I alluded to, is why does it have big things in it? Now, let's talk about something like the Earth. Why is the Earth big? What sets fundamentally the size of the Earth? If you look at all the rocky planets in the solar system, they all have roughly the same size. Why? Well, there's actually a natural scale associated with the following phenomenon. Let's say you make an aggregate of rock or material of any kind. It can keep growing and growing and growing, but at some point there's so much mass that there's a gravitational pressure that wants to crush it, and what's holding it up are the atomic forces that want to the electric forces ultimately coming that control atomic pressure. And it's a balance between these two pressures that sets the size of the Earth. In fact, you can do a very simple estimate that says that the ratio of the size of the Earth to the size of the atom is exactly the square root of the ratio of the strength of the electromagnetic to the gravitational forces. The ratio of the strength of those forces is 10 to the minus 38, around 10 to the minus 36. And so if you take the square root of 10 to the 36, 10 to the 18, indeed, the size of the Earth is around 10 to the 18 times the size of the atom, which is 10 to the minus 8 centimeters. Okay? So the Earth is around 10 to the 10 centimeters big. So in other words, the fact that the universe has large things in it is a reflection of how weak gravity is compared to the other forces. Okay, so now we can ask, why is gravity so weak compared to the other forces? Well, it's because the masses of the elementary particles are very small compared to the Planck scale. If the masses were much bigger, gravity would get stronger and stronger. And in fact, if the masses were near the Planck scale, gravity would be the dominant force. Okay, so all right, so now we keep transmuting the question. So why are the masses of the elementary particles not near the Planck scale? Well, the thing that sets the masses of the elementary particles, remember, the entire question of how we interpolate between massive and massless have to do with the Higgs particle. So the Higgs particle had to come in at some scale to allow us to go from the world of massive particles at low energies to massless particles at high energies. And therefore, the masses of all the elementary particles are actually pegged to the mass of the Higgs. If I move the mass of the Higgs up and down, the mass of all the other elementary particles would have to move up and down with it. Okay, so that's the importance of that's the fundamental importance of the Higgs. So we've managed to transmute the question of why the universe has big things in it to the question of why does a Higgs particle have a mass that's so much smaller than the scale associated with gravity, the Planck scale. Now, before getting to that question, let's ask a seemingly related question. After all, we have particles that are just massless. They don't even have mass, like the photon. So do we understand why the photon is massless? And in order to see why there's an issue, you see, if the photon is moving around through the vacuum, it can have all these complicated interactions with virtual particles in the vacuum. I've shown a particularly complicated one in this picture. And so there's a principle that's called the totalitarian principle in quantum mechanics. It says that that which is not forbidden is compulsory. So if there's no reason why the photon can't have a mass, even if in a classical theory you would say, well, I decided not to give it a mass. Quantum mechanically, everything that's not forbidden is compulsory, and some of these interactions with virtual particles in the vacuum should give it a mass. Okay, so but the photon is massless. So why is that? And in fact, there's a good reason why the photon is massless. The deep reason why the photon is massless is that 2 is not equal to 3. And again, it goes back to space-time and quantum mechanics. Remember, I told you that the number of degrees of freedom for a massless particle with spin is 2, while the massive particle with spin 1 is 3. And so if any approximation the photon is massless, none of these interactions, its masslessness is robust. None of these interactions, no smooth deformation of the physics can turn 2 into 3 discontinuously. And therefore, the masslessness of the photon is something we understand. The same thing is true for the graviton, but not for the Higgs. That's the deep problem with the Higgs, is that the Higgs is an elementary particle of spin 0. It's the first elementary particle of spin 0 that we've ever seen. And many people thought that we shouldn't see elementary particles of Higgs of spin 0 for precisely the reason that I'm about to explain. A particle of spin 0, there's no difference between the number of degrees of freedom of it when it's massless and it's massive. And so this is the leading interaction. There's a particle probably many of you haven't heard of called the top quark, which has the largest coupling to the Higgs. That's why I've drawn it here. But this very simple interaction between the Higgs and virtual top quarks would just give the Higgs an enormous mass. There's nothing that the totalitarian principle does not stop. It in fact demands that the Higgs should have a mass. And there's no other fundamental scale that we know of other than the Planck scale. So that's our first estimate. The analog of the estimate we did before for the energy density of the vacuum would lead us to expect that the Higgs might be enormously massive, might be Planckian. Okay, so all right, so those are our problems. We don't understand why the universe is big and why it has big things in it. Now, for 40 years, people thought of one approach to this problem, especially in the context of the Higgs, which is in this picture, trying to find the analog of a pencil, of a hand to hold up the pencil, find a dynamical mechanism that would actually remove these violent space-time fluctuations that would of the sort that I drew here associated with the Higgs. And again, the problem of these fluctuations is a very structural one. So it stands to reason that a good solution to it would also have to be pretty structural. And we can go back to our menu of possibilities and see that there's one last possibility that was not used, which is to have elementary particles of spin 3/2. It turns out if you have massless elementary particles of spin 3/2, again, some high energy approximation, that's only consistent if the universe has a certain doubling in it. Okay, and that's associated with the notion of supersymmetry. Now, one way of characterizing supersymmetric theories, it's a very convenient way of thinking about what's going on. It's not necessary, but it's a convenient way of thinking what's going on. Is that in addition to our ordinary dimensions of space, we also have some other dimensions, but these aren't kind of like boring extra dimensions that are just like some of our own that we curl up in some way. they're more interesting because the distances in these quantum dimensions are not measured by ordinary numbers. They're not measured by commuting numbers. I mean, if I have a distance in the x and the y directions, ordinarily, of course, dx times dy equals dy times dx. But the distance in these quantum dimensions anti-commute instead. So the product of the distances in the x and y directions, or any two directions, is negative, reversing the ordering. And so in particular, it means that the square of a distance in any given direction is equal to 0. Now, what that means is that I can imagine a particle moving around in our ordinary dimension, but let's say I'm trying to sort of doing a Taylor expansion of motion in the quantum dimension. Because of this feature that the distances squared are 0, the particle can't take more than one step in the quantum dimension. It can't take 17 steps. It can only take one step. When it takes its one step into the quantum dimension, it would be interpreted in the ordinary 4 dimensions as being a supersymmetric partner, the super partner of the ordinary particle. So we'd have an electron and we'd have a supersymmetric partner of it, where the electron takes its one step in the quantum dimension. Now, as I mentioned, this turns out to be a necessary structure if you want to have elementary particles of spin 3/2. But why does it solve this violent quantum fluctuation problem? The reason is, if we imagine going back to our picture of the box and making the box smaller and smaller, imagine at some point the box gets small enough that you actually see, you're able to excite things in the quantum dimension. Another thing I should have mentioned up here is that there's supposed to be a symmetry between the ordinary dimensions and the quantum dimensions. Well, as you make the box smaller and smaller, we have these more and more violent fluctuations, but at some point you see the quantum dimensions. There's supposed to be a symmetry between the quantum dimensions and the ordinary dimensions, but you can't have violent fluctuations in the quantum dimensions because you can't even take more than one step. You certainly can't go up and down and up and down and up and down. And so since there's a symmetry between the quantum dimensions and the ordinary dimensions, that means that there can't be any violent fluctuations in the ordinary dimensions either. And so technically, the presence of these doubled spectrum, these superpartners, cancels all the quantum fluctuations associated with the ordinary ones once you see them. Okay, so that was a paradigm for what was going on, is that we should find some mechanism to stabilize the Higgs, to remove these quantum fluctuations, and that notice that this made a prediction that you have to see whatever this mechanism is, whether it's supersymmetry or not, whatever this mechanism is, you have to see it at around the length scale associated with the Higgs, at around 10 to the minus 17 centimeters. If it only shows up at 10 to the minus 20 centimeters, then you still have the problem of something violently fluctuating massively more than it should, and it only gets stabilized at much, much shorter distances. So this made a prediction that not only that once we see the Higgs particle, we have to see other things coming along with it. The Higgs shouldn't be lonely. Supersymmetry is a particularly dramatic example of other things that should come along with it, but the basic paradigm of finding some mechanism to stabilize these violent quantum fluctuations predicted that the Higgs should not be lonely. It should come along with lots of other particles that give you a mechanism to sort of stabilize it and explain why its mass is stable against these violent quantum mechanical fluctuations. And of course, famously, what's happened in particle physics over the past 10 years is we discovered the Higgs on July 4th, 2012, as I told you, and we haven't seen any other particles since, any other new elementary particles since. So that means that that this whole paradigm that something has got to remove these violent quantum mechanical fluctuations is essentially disproven. Now, it's not completely disproven, but I would say that if you turn into a pumpkin, if you're Cinderella and you turn into a pumpkin at midnight, it's 11:55. Okay, it's really very, very late for things to start showing up. Another indication that there is something wrong with this basic paradigm is that this basic paradigm also would make a prediction in the case of the cosmological constant. Remember, that was an even more violent problem, 10 to the minus 120. The problem with the Higgs is like a 30 order of magnitude problem. The problem with the cosmological constant is a 120 order of magnitude problem. But the length scale that's associated with the energy density of the vacuum, and I should have also mentioned that people wanted for many years they had a sort of fantasy that this problem of the cosmological constant was so severe that some amazing mechanism would explain why it's exactly zero, right? We'll discover some incredible mechanisms someday that would tell us why it's exactly zero. And yet, when the astronomers discovered the universe is accelerating, the simplest explanation for the acceleration is that the cosmological constant is non-zero. And it is just around 10 to the minus 120. Okay? So we even have an indication that the size of the vacuum energy is not zero, but the length scale associated with it, it would be around a millimeter. Okay? So it's and we can all do the experiment to see there's no new physics at a millimeter just by putting our fingers very close to each other and looking. So we have this very basic fundamental problem that quantum mechanics, and because of quantum mechanics in space-time, we expect more and more violent quantum fluctuations as we go to shorter and shorter distances. That should destroy all macroscopic order in the universe. And yet here we are, we have a nice huge universe with very weak gravity that allows large objects like you and me, the Earth, you and me, and so on to exist. Okay, so and this basic paradigm of some kind of mechanism to stabilize it, which already fails for the cosmological constant, appears to be failing also for the Higgs. So we don't know what to make of this. This is it's a big shock to many people, not everyone, but it was certainly not the sort of prevailing paradigm. And another point of view has emerged, which also involves a change in our notion of what space and time looks like in order to deal with these problems, but in a radically different way, which is to actually assume that maybe what we see in the world around us is not isn't what it looks like everywhere, and that if we zoom out from some sort of God's eye picture and look out at really enormous scales, we might see that our universe is actually a tiny part of a vast multiverse. Now, the idea here is that all of these regions in this bigger multiverse, they would have the same relativity in quantum mechanics, but they have a different menu of possibilities, okay? A different menu of particles, strengths of the interactions, maybe even the dimensionality of space could change from place to place. And this picture gains some support from developments in string theory in the 2000s, where there's an example of a theory that appears to be unique, one underlying theory, but the theory can have enormous space of solutions. And any given solution corresponds to a vacuum that would look like one menu of possibilities, but you can have lots and lots of them. And really, it's continuously infinitely many of them, but depending on what you condition on, let's say 10 to the 1,000, 10 to the 10,000, just gigantically a huge number of different possibilities. These huge numbers arise basically because of exponentiation. You have many choices you can make for how you curl up the extra dimensions, and the number of choices quickly grows exponentially in size. Now, if something like this was true, then you could imagine the following completely alternate explanation for why our vacuum energy is very small. You could wander around the universe, this multiverse, and look around and say, okay, here the vacuum energy is as huge as you thought, it's Planckian. But the world is curled up at the Planckian scales and it is doubling in size. It clearly is empty, nothing is going on there. But even if the vacuum energy was like 10 billion times smaller than that, still the universe would be accelerating so tremendously rapidly that it would rip all the structure apart. In fact, if you look around, if you take our universe and you just imagine that the vacuum energy was only 5 or 10 times bigger than what we observe it to be, then even locally around us, the acceleration that would be caused by that vacuum energy would rip apart galaxies before they had a chance to form. So you can look around and say, look, in all these places, the vacuum energy, here it has its natural value, here it's 100 times smaller. Why can I find one 100 times smaller? Because there's 10 to the 1,000 possibilities. Just statistically, there'll be one that's 100 times smaller, empty there, 1 billion times smaller, empty there, empty, 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 until you find these tiny regions where, by completely accidentally, but statistically possible, because there's 10 to the 1,000 different possibilities, there's a region where the energy density is 10 to the minus 120, well, it's also the only one where the universe is not empty. Okay, so this kind of reasoning is sometimes called anthropic reasoning. And this was a possible explanation for the smallness of the cosmological constant that was put forward by the great Steven Weinberg back in 1987. And it's the only scientific explanation that we have at the moment for the smallness of the cosmological constant. Maybe we'll come up with an explanation of this sort maybe we'll come up with another explanation someday, but this is definitely a possibility that's worth taking seriously. And this picture arises easily in a lot of pictures for deeper pictures for fundamental physics. The prerequisite that we have lots and lots of different possible vacuums we seem to get in string theory, and even though there's a natural mechanism for sort of populating all these different regions using the ideas of inflation in the early universe. So I think the picture both arises reasonably easily, and at the same time, there's something very peculiar about it. All these other vacua that are supposed to be out there, for like precisely the reason that our universe is accelerating, light from them can never make it to us, and so we can literally never see them. So we're using the existence of things outside our cosmological horizon that we can't even in principle see in order to explain something about a property of our universe. That's suspicious. It's not clearly wrong, it's not clearly right, but what I actually like about this entire way of thinking is that it exposes at the same time all of the conceptual mysteries about space-time and quantum mechanics. And I think there's a lot of reasons to take it seriously, but it's not a theory yet. It's only a cartoon for what might someday turn into a theory. But there's a lot of features of trying to make sense of this cartoon that are useful and force you into thinking about new lines of research about some of these questions. Okay. Now, could we get any more evidence for something like this? And I'll just end with this. You might ask if something like this landscape is responsible for the smallness of the cosmological constant. What about the Higgs? And in fact, there's a similar issue, not quite as dramatic as the universe being empty. But remember, we just said if the vacuum energy was just a little bit bigger, the universe would be empty. What would happen if the Higgs particle was a little bit more massive? Then as it drags, remember I told you, as you drag up the mass of the Higgs, you drag up the masses of the rest of the elementary particles. And then if you just drag up the masses by a factor of 2, something 2 or 3, something relatively dramatic does happen. You all know that the complicated nuclei are made out of neutrons and protons, but you also know the neutron is heavier than the proton, and in empty space, the neutron can decay to a proton. So why doesn't why do we have a nuclei made out of neutrons and protons if the neutron can decay to a proton? It's because the binding energy of neutrons and protons inside a nucleus is actually is bigger than the mass difference between the neutrons and the protons. But that turns out to be a complete accident. And if you make the elementary particles heavier, then the quarks inside the neutron and the proton become heavier. And they make it so that the neutron-proton mass difference becomes larger than the binding energies already just if you make all the particles heavier by a factor of 2 or 3. And so that means that if we just change the situation just a little bit, we would go from having all these complicated nuclei to just having hydrogen and nothing else. So there was another sort of big difference in the world if you just made the Higgs head in the direction that it wants to head by making it even more massive. So it's conceivable that there's a sort of a landscapey way of approaching the problem associated with the Higgs mass as well. But there are a lot of beautiful things about the old picture. There's a lot of beautiful things about the supersymmetric picture I didn't have time to explain, but it played very nicely with the notion of unification of forces at very high energies and made various quantitative predictions about that at the percent level that ended up being correct. There's a picture of dark matter associated with it. I haven't had time to talk about. But there's an interesting intermediate possibility that takes the landscape seriously but says that the presence of the landscape could impact the sort of version of supersymmetry that we see, and that there could be a different version of supersymmetry that we called back in 2004 and 5 the minimal split supersymmetry, where half of the new particles associated with the superpartners are by this famous factor of Q squared, that number of around 100, 1 over 100 that I talked about, that parametric factor of 100, we make the so-called scalar superpartners 100 times heavier. The fermion superpartners would be left lying around and would be accessible at closer energies that would be associated with dark matter. This is a very unusual picture of supersymmetry. It would look fine-tuned from a conventional way of thinking about things, but is very reasonable with the landscape. And it made a correct prediction. This theory was proposed back in 2004 or 5. It correctly predicted that the Higgs particle should lie in this relatively narrow range between 120 and 135 GeV, which it did do. It was discovered at 125 GeV. So it's not a very impressive prediction, but it's at least not wrong. And anyway, that's my own best bet. If you're going to wake me up in the middle of the night and ask what I think is going on, I think some version of minimal split SUSY is probably right. But it could be that we would need to wait for the next generation of colliders to have high enough energies to make even these fermions of a SUSY. In this model, they can't be heavier than around sort of 5,000 GeV or 5 TeV. They could still be too heavy to be made at the Large Hadron Collider, but people both in Europe and in China are talking about a new set of colliders beyond the Large Hadron Collider. They'll be around 100 kilometers around and collide particles at around 100 TeV. The LHC is colliding particles at around 14 TeV. This is going to be a very big leap. You could use this big tunnel to collide electrons and positrons and produce millions of Higgs particles to put this unusual, bizarre new beast, the Higgs, to put it under a microscope and study the hell out of it. And later in the same 100-kilometer tunnel, you could collide protons up to around 100 TeV and probe what's going on with this deep question about the violent quantum mechanical fluctuations of the vacuum. The LHC is just in the neighborhood of sort of telling us there's something wrong with our old way of thinking, but not high enough energies to like tell us what's right in any very definitive way. So anyway, it's not guaranteed that these colliders will actually happen, but they're serious proposals of putting them forward. They have a chance of happening, and certainly I'm going to the gym and working out. And hoping to someday see these 100 TeV collisions, because I'm pretty sure they'll discover these particles associated with split SUSY. So I want to be alive to see that. All right. Well, I think I'll probably end there. There's the last topic I wanted to talk about, but I've already gone so far over time, so I won't talk about this. If people are interested, we can talk about it in the question session. But what I hope to have done in this talk is shown you how these deep principles of space-time and quantum mechanics dictate the properties of the world around us. I think it's an incredible story. And B, how dramatic it is that those very principles are under great pressure. And we somehow have to find a new set of ideas that tells us where those principles come from, explaining why, on the one hand, they're so stunningly successful, and yet, on the other hand, how they could be superseded by things that are likely to be deeper and more abstract as we move forward in the 21st century. Thank you very much.
Okay, so let's thank Nima for an absolutely fantastic talk. We already had
for going so long over time, guys.
No, this was fantastic.
No. Fantastic
yeah,
talk.
Yeah. So if there are any questions, you can write in chat or directly unmute and ask. Let's see if I see any hands.
So there are no experiments you think which will suggest this, excepting whatever these large hadrons and so on that you want to construct. Nothing else, because for the between the multiverse and
Well, I mean, you see, even even that, what if something like split SUSY was discovered, it would still not prove that there's a multiverse out there. In fact, that's our sort of big problem. We don't know how to build a telescope to see the other universes yet. Okay, but that might make you think, oh, it's all garbage. Probably, where it's like counting angels on the head of a pin. But it's a little bit similar to some very famous physics involving black holes. So living inside an accelerating universe is a little bit like being inside a black hole. So we have a horizon sort of outside. We can't see the things from the outside. Now, in the context of black hole physics, we've learned that classically you think you can throw something into a black hole and it's gone, but quantum mechanically it evaporates with Hawking radiation, and the information is supposed to come back out somehow. Okay, so now and exactly how it comes out and how to think about it is still under very active research by people who think about those things. But you can already draw kind of a parallel that in the same way you might think that things that are outside our cosmological horizon are sort of garbage, that we can't see them, we shouldn't talk about them, but maybe there's some quantum mechanical way that their presence can actually be seen inside our own universe. Okay, so now, but we don't know. We don't know either way. But the main problem is to build a telescope to see. Okay, and we don't know how to do that. So, but what we could do is get more examples of quantities that appear to be sort of crazily fine-tuned from one perspective, so that we can get more evidence of things that are that don't make sense from the standard perspective, but would make sense from this other perspective. It doesn't mean that it's right, but it will give more of a psychological push in that direction. So the discovery of something like split SUSY would do that in a big way, because you would actually see, you would have evidence that the world is supersymmetric, but that supersymmetry did not bother to survive to low enough energies to solve all these problems. Okay, supersymmetry could have already solved the cosmological constant problem, and it didn't. It could have already solved this other problem with the Higgs, and it hasn't. So that might just lead you to think that it's just garbage. It's not. I mean, sorry, that it has nothing to do with these problems. But if you discover that it's actually sitting there, but refusing to solve these two problems, that's even more indication that there's something else going on. I mean, now these big colliders are the most direct way of looking for the new particles, but there's actually some beautiful tabletop experiments that can also look for them. There are many of them. There's now a thriving field of sort of tabletop experiments to look for very tiny effects that would still tell us that we're going beyond the standard model of particle physics. But my favorite one is to look for some substructure associated with the electron. So, the electron has charge, and you can think of it as a little spinning top because it has spin. But it could also have a non-uniform distribution of charge, and that would show up as an electric dipole moment. Okay, so to have some. Now, there's no evidence for an electric dipole moment of the electron. If you the kind of units of a dipole moment are length, right? Because it just says how much it's stretched out. So the experimental limits on the electric dipole moment of the electron for many, many years were down to around 10 to the minus 27 centimeters. Okay, so that's that shows you how shockingly accurate these experiments are, because we are certainly not even seeing 10 to the minus 17 centimeters at the collider. Okay, so the limits are around 10 to the minus 27 centimeters. There was a real breakthrough around 7 years ago by a group at Harvard and Yale, the Acme collaboration, Jerry Gabriels, John Doyle, and Dave DeMille, and they improved things by a factor of 100 over the past 7 years or so. Factors of 10 an experiment, make a career. Factors of 100 are a real breakthrough. And they're going to go another factor of 100 in the next 10 years. Okay, so they're going to get down to around 10 to the minus 31 centimeters. The reason I bring this up is that in split SUSY, it's not a sharp prediction, but you expect that the dipole moment should be between 10 to the minus 28 and 10 to the minus 31 centimeters. from the effect of these very heavy particles, they should give a little dipole moment at that size. So you see they're down to 10 to the minus 29. So they've already cut into the parameter space a little bit, but we have sort of 2 orders of magnitude to go. And so I'm very excited about these experiments. If they see something, again, it would be sort of consistent with what we'd have expected from split SUSY. And there's some other experiments like that. But so it's not just giant colliders. Giant colliders are necessary for our business. They're really necessary. A, because we go to the high energy frontier to see what's there. But B, even without just this fishing expedition, it's really necessary to put the Higgs under a microscope and study it to death. It's a very weird particle. For the reasons I was trying to explain, we've never seen anything like it before. For very good reason, we've never seen anything like it before. And yet we've seen it. It hasn't been, its origin has not been explained in the way people expected it to be explained for 40 years. So so it makes sense to put it under a microscope. So that's the main thing that these new accelerators would do. But then beyond that, we'd also go to the higher energies just to see what is around. The time scale for those things is 20, 30, 40 years if they happen at all. So in this business, you have to get used to very, very long time scales for progress. Of course, it's something that mathematicians are very used to. One of the things I love about interacting with mathematicians is that worrying about things that might take 100 years is not a problem for mathematicians. And I think we have to get used to similar timescales in the fundamental physics. We are spoiled in the middle of the 20th century by a period of sort of very rapid progress, but it's a period of very rapid progress because it was not quite as revolutionary as the things that came before, and I suspect as the things that will come now. That progress is very rapid because the intellectual framework in which to understand things was set, and it just had to be filled in. Now we're at a moment where we have to really take another step, and so it's I think it's going to be similarly challenging.
Okay.
Any other questions? There is one by Anand. Anand, maybe you can just unmute and ask.
Oh yeah, hi Professor. Thanks so much for the talk. I had a question about how the theory of the landscape actually dooms space-time, or in other words, I didn't really understand how that theory would resolve the issues that you're talking about.
No. These are 2 separate things at the moment. Yeah, I was trying to say that there are 2 separate issues. One of them is that space-time is doomed. The other one is that we don't understand why there's a macroscopic universe. Now, having said that, you see, the problems might be related to each other, because after all, if space-time is supposed to emerge from something, even to kind of tell that there's a space-time sitting there, it has to emerge on distances larger compared to the Planck length. Okay, so something has got to explain why we managed to get a big flat space-time in order to even call it a space-time to begin with. So it's possible that these 2 problems are linked to each other, but it's also possible that they're not. They're at the moment sort of 2 distinct problems. One of them is, even given the big space-time, even given it for granted, like we don't know what happens when we scatter gravitons or scatter electrons at energies comparable to the Planck scale. Something happens. When the curvatures become large, something happens, but we don't know what. The other one is a somewhat more meta question. How did this come about to begin with? Why is the energy density so small to allow a big universe to exist? So those are 2 distinct questions.
So sorry, just to follow. So what do you think a theory that actually would explain space-time would look like? Do we have anything that you believe would really work, even today, among the ideas that exist?
Yes. Well, I mean, that was part of the kind of third part of the talk, but I already explained one. I mean, in a sense, the kind of main line of investigation, and I'm sure you'll hear more about it, perhaps from Rajesh Gopakumar's talk. As I mentioned, string theorists in the late 1990s ran into this holographic idea that the world is that, at least in these worlds that look like the inside of tin cans, we have the what you can think of as the sort of gateway drug to the idea of emergent spacetime. Okay, because there you have really a theory that is just an ordinary quantum field theory on the walls of the box but it gives rise from the strong interactions of the particles there. There's it's as a hologram, the interior. Okay, so that is an example where we can see gravity and space emerge from things that don't have gravity and space or have less space in them, you know, one lower dimension. Okay, as I said, it doesn't apply to our universe directly, and one of the conceptual reasons it doesn't apply to our universe directly is it's leaving time untouched. Time is not emerging. Only space is emerging. Time is not emerging. So in order to come up with a framework where space and time emerge, everything, my own suspicion is that we have to be looking for something more abstract, and that space-time and quantum mechanics will both come out together from these more abstract things. But there's no obviously general, correct, agreed on picture for how this could happen. There are different strategies for going about it. I have my own strategy that I've been pursuing, which is to try to take, since we're trying to get rid of space-time and maybe both space-time and quantum mechanics, to try to take ordinary physics, completely ordinary physics, these same scattering of energy particles that we just talked about, and try to reformulate it in a language where the notions of space-time and quantum mechanics don't make a primary appearance. To come up with an answer to those questions where you don't put in the picture of the particles are traveling inside space-time and colliding with each other, and that there's a weight function evolving in a Hilbert space. You don't put any of those things in. You ask a different sort of question just to directly give you the functions that are these amplitudes for the particles in going out, and see if such a thing exists. If space-time and quantum mechanics are sort of be derivative from something else, that's such a big move that it has to have echoes everywhere else. And in particular, you have to be able to talk about ordinary physics without making such heavy use of the ideas of space-time and quantum mechanics. And what we've been seeing over the past 10 years is that there are some rather remarkable new mathematical structures in combinatorics, algebra, geometry, number theory even, which allow you to do this. They allow you to ask these interesting new kinds of mathematical questions whose answer are these amplitudes. Even though there's no space-time and quantum mechanics in them, the answer are exactly what you get if you do have space-time and quantum mechanics. And you can even see what features of these mathematical structures allow this space-time and quantum mechanical interpretation. Okay? So that's my own view of my own strategy for trying to attack this problem, is to try to reformulate physics by eviscerating space-time and quantum mechanics from it, and start doing that by reformulating standard physics in this way. Anyway, that was the kind of third little vignette part of my talk I didn't get to. But but people like Alok know all about this. So if you want to hear more about it, you can certainly talk to him.
Any other questions? I don't see any hand. Okay, so maybe if you don't have any other questions, let's thank Nima once again for a remarkable talk.
All right, guys, enjoy your dinner.
Thank you.
Thank you. No, thank you so much.
Thanks, lovely.
Thanks.
Thank you.
Bye, guys.
Bye, Nima.
Bye.
Hey, I'll talk to you on Thursday, okay, Ella?
Yeah. See you on Thursday. Bye.
All right, see you. Bye.
Thank you.